let me now move on and introduce today's speaker, Joe Stroscio. It's great to have you here. Thank you very much for accepting. And again, I think I've been saying this a couple of times already, but let me say it again. I think today we again have a speaker that doesn't really need an introduction for this audience. But in case somebody has not heard of Joe Stroscio, let me very briefly introduce him. So he got his PhD from Cornell University, and I believe he was Wilson Ho's first graduate student there, if I understood correctly. And he was working on high-resolution electron energy loss spectroscopy. He then moved to IBM Watson Research Center to work with Randolph Feenstra, and that's where he got started with STM and scanning probe microscopy and spectroscopy. And then in 1987 he joined NIST, and he is there. He's a NIST fellow at the Nanoscale Processes and Measurements Group today. Well, there's a broad range of different kinds of experiments that his group is performing, but he leads multiple projects in nanoscale physics and technology. For example, things like atom manipulation, physical properties of nanostructures, nanoscale magnetism, epitaxial growth of metal and semiconductor systems, and now in the last, I don't know, about 10 years, also low-dimensional electron systems in graphene and related 2D materials. And I think one of the particular things about Joe and his colleagues is that they have designed and constructed numerous state-of-the-art scanning probe systems that operate, of course, in ultra-high vacuum, but ultra-low temperatures and in ultra-high magnetic fields. And today, the title of his talk is a microscopic view of graphene quantum Hall edge states with STM and AFM measurements. So with that, we very much look forward to your talk. Please.
Thank you, Peter, for the kind introduction. I think sometimes you get more known just because you're older. But anyway, yeah. So today's talk, I'm going to talk to you about the microscopic measurements of quantum Hall edge states. When I gave this title, I was thinking more on the recent work we've done, but when I put the talk together, I included some older work to make sort of a tutorial on p-n junction work that we've been, p-n junction systems and graphene that we've been probing for the last few years. So I wanted to thank all the people who contributed to this work, all the young people on the team do all the measurements. I'm just kind of like the technician who kind of keeps the machines running. There are a number of references for this work here below. You can look up. The first few references cover the circular p-n junction resonators, and the last one is the edge state work in the quantum Hall systems that's coming out next month. And a number of collaborators I work with in instrumentation: Franz Giesebel, Hans Hug, and the quantum Hall system was done in collaboration with Corey Dean's group, and we've gotten a lot of theoretical support for Leonid Levitov at MIT. So this is the outline of my talk. I'll just give a first few words on graphene just to get you oriented in that space. And then the talk is in two parts. First, we'll look at circular graphene resonators, p-n junction resonators, where we'll look first at the harmonic oscillator states you get in those, and then the low field and high field behavior where we transition into Landau levels. Then we'll see similar physics happening in rectangular p-n junction Hall bar, where we'll see the same kind of Landau level formation happening. But here we're going to use AFM measurements now in a new instrument where we combine STM, AFM, and transport measurements. And here we can actually use the AFM itself to measure the energy levels of the quantum Hall states and map their spatial dispersion through the quantum Hall boundary. So I hope you enjoy the talk. It's a fairly lengthy talk, but I think it's well integrated, and I set it more as a tutorial for you. So a few words on graphene to get you oriented. Graphene is a wonder. It's a wonder material. It's recorded more than 4,000 years ago. It's been used as a pigment in ceramic paints. And we know, since the last, since 2005 now, more than 15 years ago, we can exfoliate single layers of graphene, and that started the whole van der Waals materials revolution. And just when you thought maybe graphene kind of was done, we've seen now in the last few years, all new physics come out of this quantum reconstruction, which I call it, where you can twist graphene heterostructures and form completely new quantum phases, as this magic angle work done by Pablo, which you heard about in one of your colloquium talks, where you get all new types of emergent physics coming out at these magic angles close to 1 degree. Important things we need for this talk is that graphene has this two interlaced lattices, the AB sublattices. That gives rise to the pseudospin degree of freedom in graphene. And the important thing, the other important part, is that we have this linear dispersion at the K points. The last few things we need to know is that the pseudospin is locked to the momentum in graphene. That's an important point. And then that we have this Berry curvature at the Dirac point due to the conical dispersion. So these two things combined together give rise to the fact that you can only get two values of Berry phase in graphene. You can either get a Berry phase of 0 if the momentum space orbits do not enclose the Dirac point, or you can get a Berry phase of pi if your momentum space orbits enclose the Dirac point. So you can either get pi like Landau levels if you go around the Dirac point, or you can get 0 if the phase space orbits don't. So this is like wax on, wax off. You know, if you were a fan of the Karate Kid movie, wax on, wax off. Then the Berry phase, then in the Landau levels, the Berry phase of pi eats up this 1/2 that you get in the standard Landau level configuration and gives you this lonely n here. So you have an n equals 0 Landau level from the Berry phase, the pi Berry phase. And then the square root dependence of the eigenvalues here in the Landau levels comes from the linear dispersion. So you get this new n equals 0 Landau level at the Dirac point, and then you get this unequal spacing in the Landau levels. That's another thing we need to know. And then if we look at how those Landau levels behave near a boundary, we know that they'll follow the potential boundary near an edge. So near an edge of a device here, you'll have a confining potential, and then those Landau levels will follow that confining potential. And when they intersect the Fermi level here, you get these one-dimensional edge states. But here you have a high degeneracy here, a lot of density, but you have a high electric field here. And so that density is going to try and screen that large electric field, and that'll bend over the Landau levels here and form these series of plateaus, this so-called wedding cake structure or staircase structure, which was pointed out in the early 90s for the quantum Hall effect. So in fact, near the edge, you'll get these regions of compressible and incompressible strips. The compressible ones are the metallic ones. The incompressible ones are the insulating ones. So we'll see how we can measure those both in STM and AFM measurements. The last thing we need to know about graphene is that it's a fourfold degenerate system. The n equals 0 Landau level has been of interest since the beginning in terms of this quantum Hall ferromagnetism. So depending on the configuration of the spin and valley degrees of freedom, you can get different ground state properties. So depending on how these order, and the order is given by a balance of the anisotropy energies and electron-phonon coupling and Zeeman energy, you have a delicate balance which can lead to a number of different ground state phases. You can, for example, if you had a polarized spin system here, you would have a ferromagnetic phase. If you had an anti-parallel spin system, you can get an anti-ferromagnetic phase or canted anti-ferromagnetic phase, and you can get also Kekulé or charge density wave phases. So it's been of interest for a long time is what is the ground state of graphene in this n equals 0 NLL? What is the actual spin and valley configurations? And each one of those ground states leads to different edge state configurations. For example, if we have a polarized spin system, we would have a ferromagnetic phase, and that would lead to a gapless edge state at the boundary. If we had a completely gapped system, for example, like an antiferromagnetic phase, then we would have a system that's gapped in the bulk and all the way through the edge. Now we know from resistance measurements that we get this high resistance at n equals 0, so we know the system is gapped. But recent experiments have shown that, in fact, you can see as a function of tilting angle, tilting magnetic field, you can actually see the gap open and close as a function of tilting angle. And that is pointed towards a canted magnetic ground state. So all these things are, what we hope to do is be able to map both measure these energies and map these states across the boundary and see if we can see something related to this physics. So this is kind of like the summary of the talk, the outline in kind of picture form. We're going to start with a confining potential in a circular geometry. We're going to look at the harmonic oscillator states. Then we're going to turn on a magnetic field. We'll see some interesting Berry phase physics happening. And then eventually those atomic shell states in the resonator will transition into Landau levels. And how that actually occurs, is a subject of interest. That's like the Falk-Darwin problem. But with these local probes, we can actually probe all those eigenstates inside the dot, follow them as a function of field. And then we'll see how these edge states then form at the boundary of the quantum Hall boundary system, and we can then map those edge states through the bulk and edge of a quantum Hall system. So that's the outline. So first, let's look at the circular geometry. So we'll look at, we'll make a circular p-n junction in the graphene. We'll look at the low field and high field behavior, and we'll see some interesting physics happening. So you can combine charge carriers in a number of ways. You can carve out a piece of semiconductors, but the more widespread use is actually to use electrostatic confinement. For example, in a two-dimensional electron gas, you can confine the electrons at an interface between gallium arsenide and L gas. And then if you pattern that with top gates, you can further confine it spatially and create a quantum dot. Or you can create coupled quantum dot, and this has been used a lot in, for example, quantum information systems today. So the question is, can we use the same electrostatic gates or electrostatic confinement in graphene? And what you'll see is that the answer is yes, but it's not intuitive because you have Klein tunneling in graphene. So your naive thought is that, well, if I have complete transmission through a potential barrier, how can I confine anything? So because of the conservation of pseudospin, you get 100% transmission at normal incidence. But what you find is that only occurs for normal incidence. And at high angular scattering, you can get the transmission is very much reduced, and you can then confine carriers. You can quasi-bound states through high angular scattering. And that's shown nicely in these simulations that my colleague Daniel Walkup has done. So let's look at how this works. So these are wave packet simulations where we're shooting a wave packet at a potential step, first at normal incidence. Here you see the wave packet go right through the step. Here you can see the wave function. You can see the change in wavelength here through the potential barrier. If we now take that same wave packet and we shoot it at an angle, we get a substantial reflection and refraction. And the refraction is this negative index of refraction that you get in graphene. So if we then can use that high angle scattering and we make now a p-n junction boundary, we make a circular potential and we scatter the wave packet, you see you get these long-lived quasi-bound states inside this circular potential. So these are essentially the harmonic oscillator states for the Dirac fermions. And what I'll show you is that we can actually probe all those harmonic oscillator states with the STM measurements, spectroscopy measurements. So first, let's see how we make them. We first have to make a graphene device, as we normally do, as everybody does. We put graphene on HBN on top of SiO2. We do one thing that might be a little different is that we build a runway for the STM. So we have to find this 10 micron device in a macroscopic area that's, which you can't see by eye. So we build out a runway which extends out into macroscopic dimensions here. And so we can then align our probe tip optically on this big runway. And then we land somewhere on the runway, we have ridges built into here, and we can navigate along one of these ridges down into the graphene area. So it's kind of like it's like you have to fly blind, but we're flying blind, but we know where we can find where we land, and we can find a fiducial ridge here and then do an automatic tracking down into the graphene. And we can do this because our STM modules are modular. They come out of the cryostat at room temperature. So at room temperature, you can do this optical alignment here. And then the STM is simply just lowered into the cryostat, locked in there and cooled down, and then the measurement begins. And then we find the runway and then follow it down into the graphene area. Then we have to perform our spectroscopy, this is how we do it. You can call this density mapping spectroscopy because now we have a backgate. And so you can take spectra as a function interleaved with the backgate electrode here. And you can create a spectral map. You can do that as a function of position. And so then you can create a map that's the function of spatial position, energy, magnetic field, and density. So this is really an LDOS measurement in this fourfold manifold. So we don't see well in fourfold space. So we typically show this in 2 dimensions. We pick out 2 variables, for example. In this case, this is bias energy, and this is gate voltage or density. So to understand this map, just remember that 0 is the Fermi level. So at negative voltage, we have hole doping. The Dirac point is above the Fermi level, so it's hole doped. And then as we go across here, we're increasing the doping level till eventually we get to electron doping. So that's why all the features go down in gate voltage, because the Dirac cone is shifting down. So here we have electrons filling up here. And this is what would happen in a bias versus gate map. The other thing is we turn on a magnetic field that quantizes the levels into highly degenerate Landau levels. And we can see that, for example, if we pull one line, spectral line out of here, we can plot that spectrum and we can see the Landau levels. So in this talk, I'll show you a number of these maps, and we'll pick out 2 of the variables at a time. So this was energy versus gate voltage, but I can also fix, for example, the gate voltage and plot as a function of distance, or I can fix the distance and plot as a function of magnetic field. We'll see all 3 of those combinations, so it's important to examine. I'll point out what is being plotted so you understand what we're probing. So this is really LDOS mapping in this fourfold manifold of space. So we have to create the PN junction, and I'm not going to go into great detail. You can look at the references, but we're using a recipe from the that was developed in Cromie's group, where we ionize defects, native defects that are in the HBN layer. So if you pulse the tip at a high potential, you ionize these defects, and the defects create a fixed polarization in the HBN insulator, which stays there. And the direction of the polarization depends on the sign of the gate voltage, which you had active during the pulse. So you can create a PNP junction, as you're shown here, or if I switch the polarity of the gate voltage during the pulse, I can create an NPN junction, where the harmonic oscillator potential is concave this way. And for these measurements, I'm going to show you a p-doped quantum dot where the potential is in this direction. Then we're going to, so this is a very general method where you can essentially use the probe tip to write any kind of doping pattern. We've written, for example, multiple quantum dots this way. But for today's talk, I'm just going to show you one dot. Then we're going to turn on the magnetic field, as I said, and we'll see how these evolve into Landau levels and how interaction physics comes into play as we have these highly degenerate Landau levels. So first, let's look at a single spectrum here. I have the probe tip parked in the middle of this p-doped island. I take a spectrum here. This is the bias. This is differential conductivity, and you can see a number of resonances here. So all these resonances are just these quasi-bound resonances of that simulation that I showed you of the dot to begin with. Now, they're special ones because they are taken at the middle. So these are all m = 1/2 states. If I move the tip horizontally, I can take spectrum as a function of radial position and plot a new map where I combine all these spectra as a function of position, and I make a spectral map with now distance is on the bottom axis, okay? Here you see the harmonic potential here, and now you see a whole bunch of modes here in the middle. So this is the complete like wave function map of this quantum dot, which you can only measure because it's graphene and exposed at the surface. So that's one of the things I should have stressed at the beginning, is that one of the beautiful things about having a graphene 2-dimensional electron system is that you can access all this physics with local probes. Decades ago when everybody was studying 2-dimensional electron gases, those were all semiconductor buried systems, 100 nanometers buried below the surface, which were difficult to probe with local probes. Having graphene allows us to measure inside the quantum dot. Now, what you see here are different eigenstates, which have a radial quantum number n and an azimuthal quantum number m. And you can index all the modes there. So the m equal 1/2 have a maximum here in the middle. So you have like n equal 1, n equal 2, n equal 3 with m equal 1/2. And then you have kind of arcs of common n values with higher angular momentum. So the higher angular momentums don't have a maximum in the center, and they form arcs here. So you have an n equal 2 arc with different angular momentum states going like that. So as I'll show you later, to probe those higher angular momentum states, we have to move the probe tip off center. So we have to kind of measure somewhere here to access these higher angular momentum states. But now we can then look at how these states evolve in a magnetic field. So now I'm going to go back and fix the position to 0, and I'm going to change the variable to magnetic field. And we're keeping the gate voltage fixed because that defines the parabolic potential. So we keep that fixed. So here we're taking just the center spectrum here now and making a new map where we're varying the magnetic field. Okay, so if I vary the magnetic field up to about a Tesla, I mean a tenth of a Tesla, nothing much happens. All the eigenstates stay flat. If I go just a little bit further, suddenly new states appear. And this is very unusual for a new state to just jump out of the ether. And it's, usually if you have a magnetic field effect, you'd have like a Zeeman splitting where something varies from B equals 0 on upwards. But this is a very large energy scale here, tens of millivolts. So this is a big jump. So this is like Wile E. Coyote jumping off the cliff. So I don't know if you're a fan of Wile E. Coyote, but I buy everything from my Acme, company. I'll explain that these actually come from one of the particular M states gets a Berry phase jump of pi. That Berry phase jump of pi causes the momentum to jump of one particular M sign of M for a particular magnetic field. So let's see how that comes about. So this comes back to the wax on, wax off picture. So as I mentioned, for Landau levels, you have cyclotron motion around the Dirac point. And the way you figure out the Berry phase is you look at the phase space orbit here, and you look at the solid angle of that orbit. So for Landau levels, that would be a solid angle of 2 pi, and the Berry phase is then omega divided by 2. So that gives you a pi. If we look at these quantum dot orbits at low fields, the momentum space orbit is completely outside the Dirac cone. It doesn't enclose the origin. So the phase space here is 0. So the Berry phase is 0. But at some point, for a particular M state, if you work out the Lorentz force here, V cross B, you'll have a Lorentz force which will bend that trajectory out into the outer turning radius and eventually cause that momentum to go 0 and switch sign. What that means is that phase space orbit then encloses the Dirac point. And at that point, you have a phase volume of 2 pi, and you get a value of pi. So at this critical field, which you can just solve for when the momentum goes 0 at this outer turning radius, at that value, you have a pi turn on of the Berry phase that necessitates all the momentums to shift for that particular M value. So we have our wax off 0, wax on pi. This shows you a simulation again by Daniel, showing you how these classical orbits vary with magnetic field. And then we plot the kinetic energy here on this Dirac cone, and you'll see that for one orbit, this one, you'll see this outer turning radius point where the angular momentum goes 0 and switches sign, and that orbit will then go across the Dirac point. This other one is winding in such a way where the magnetic field just keeps winding it tighter and tighter. So that one, the Berry phase doesn't change. So let's see how this looks. So here's the magnetic field going up. If you watch this one, suddenly at this point, angular momentum is going, the momentum is going to zero. A switch sign, you created this loop here, and the Berry phase has jumped up, and this orbit had just gone over the Dirac point. So now the phase space volume here is 2 pi. The Berry phase has to switch to pi. So one eigenstate gets jumped in energy and one stays constant. That's why we saw this doubling of the eigenstates as a function of field. So now the other prediction of this critical field is that it should depend on the angular momentum number, m. So with higher m values, the critical field should be higher, as shown in these simulations by Levitov's group. And so we can look for that by doing that same measurement I showed you at the beginning, but now parking the tip off center. And that's shown here at the left. And you can see many jumps now. And if we just plot this expression for the critical field here by the dashed lines, you can see it agrees extremely well with all those critical field values. And we can see switching behavior all the way up to m equal 9/2. So this shows you very nicely the Berry phase physics in these graphene quantum dots that you can access completely with the local probe measurements. So now we can ask the question, what happens if we go further in magnetic field? Where do Landau levels come from? So now this is the Falk-Darwin problem where somehow we have to take these atomic shell-like states and condense them into Landau levels. And how does that happen? Does it happen, on the out? Does this happen uniformly through the dot on the outside or the inside of the dot? So that's an open question, and we can actually see that with local probe measurements. So we'll simply take these maps now, and we'll vary the magnetic field. And then the field we expect something to happen is when the magnetic length is on a characteristic scale here, which is on the order of maybe 50 nanometers here. And that field length, that field scale should be on the order of 0.5 Tesla. So we should see something change on the order of 0.5 to 1 Tesla. So 1/4 Tesla, we just see the Berry phase doubling here. 0.5 Tesla, we kind of start to see some bright increase in density here at the center of the dot. And then that just gets more pronounced here at 1 Tesla. So this is the beginning of the Landau levels. So we see kind of like the Landau levels eating the atomic shell states in the center of the dot, and we're forming well-defined Landau levels. So we see that this condensing is happening in the middle of the dot and moves out. So we go to higher field, it moves out, goes to higher field, and moves out. We have less quantum dot states. The other thing you see here now is that the Landau levels are making a hat-shaped pattern. And that gets more developed with increasing field. And you can even see some funky behavior here, which on top of these hat-shaped Landau levels. And then finally at like 4 Tesla, you can see this hat-shaped is well-defined. So now this hat-shaped is just that compressible, incompressible strips that I talked to you about in the beginning that was predicted early in the quantum Hall research. So what's happening is that the parabolic potential here is getting reconstructed due to the fact that when I form these Landau levels here, I have a high density of electrons, I have a high electric field. That's going to bend over the potential here, and you're going to reconstruct the potential in this form here. This is shown by calculations. You can find them in this paper here that we published. But you end up with these compressible rings, compressible disks, when the Landau levels are at the Fermi level. So here's a compressible disk here, here's a compressible ring. And a proof of that is if you, and then you can show that in the calculations. If you take electron interactions into account, you can reproduce this kind of wedding cake structure. But what I want to show you a little more, which is a little more interesting, is that these compressible structures are Coulomb islands in themselves. So now you have an isolated Coulomb island separated by an insulating region. They're going to act as a quantum dot in their own right. And you can see that already by these kind of faint lines. These are Coulomb charging lines where you're seeing Coulomb charging of those compressible Coulomb islands. And if we go to 8 Tesla, that becomes dominant. So if I park the tip over the center of the island and I do this spectroscopic map again, you can see that the whole spectral map is dominated by Coulomb charging features instead of Landau levels. So Landau levels are even hard to see. They're these broad things here. Instead, you see these sharp lines. Each line is then adding a single charge to the Landau level quantum dot. So this is now not the quantum dot we started with. This is now essentially Landau level quantum dots inside the confining barrier. So initially you'll have like a disk here where the Landau level just hits the Fermi level. This is the first hole you add to that disk, the second one, the third one, etc. Eventually that Landau level will punch through. Remember, as we go down, the Landau levels go up, and then the sides of that will form a compressible ring. So this disk becomes a ring. At another gate voltage, eventually the second Landau level pops up and forms another disk inside this ring. So we have a double quantum dot. You can measure all the properties of this quantum dot. You can measure the slope from this is the plot through the lines here. You can measure the radius, you can measure the charging energy. When you get two dots together, two compressible islands together, they're actually coupled. And so we see two charging lines here. We see a bright series here, but you still see the fine series from the original dot here on the outside. And if we look closely in this region here, this is shown here, you essentially have an avoided crossing between these two charging events. And this is like the classical double quantum dot physics. So we can actually engineer multiple quantum dots out of these compressible islands. And I don't have time to talk about that, but you can look at Daniel's paper here, which discusses this in detail. So I hope you enjoyed that tour of circular PN junctions. It was kind of quick, but what I tried to show you is that we can engineer these harmonic oscillator states. We can look at the low field behavior where you see this interesting Berry phase. And then finally, we can develop the Landau levels, and they form these compressible rings and disks. Now we want to look at those same rings and compressible regions now, but at lower temperatures. We want to go to higher resolution to actually look at this quantum Hall states, how the degeneracy is lifted, and we need to go to lower temperature to get better resolution. And to do that, we actually built a new instrument to do that, where we combined AFM, STM, and transport measurements. And so I'm just going to spend a few slides to introduce that to you. I'm going to go fairly quickly because that's just kind of an instrumentation. But the motivation for that was that, especially now in all this twisted physics devices, you see a new measurement coming out every day. But you can see that every measurement is different from the day before. So starting with Pablo's discovery here of the superconducting insulating phases, the devices got improved, and you can see many more phases. Is this due to better angular homogeneity? You can see different physics come out if you have the graphene and the HBN Moiré lattice, superlattice. So if I were to do a measurement on this structure, which measurement should I compare it to? And the answer is you don't know unless you do the measurements together. And so we built a machine to do that, so we can do both transport measurements and microscopic measurements together. And so Franz Giesel came and spent a sabbatical with us 4 years ago. He taught us how to do AFM and designed a new AFM sensor for us to put in our dilution refrigerator here. This is Sigmund Kim and Johannes Schwenk, who were the lead guys doing all this instrumentation. And then this is kind of like a summary of that instrument. We had to re-engineer, built a whole new module, multi-contact tip and sample holders, so you can do the transport measurements as well as the Q+ sensor, improved RF filtering here so we can get better energy resolution. And you can find a detailed description here of all the little tricks in this RSI paper. So the AFM works as good as we hoped for. It can do atomic resolution mapping, it can do Kelvin probe mapping, as I'll show you later. We get Qs over 100K typically. Franz designed a new Q+ sensor for us because I didn't like the shaking piezos with an integrated electrode. So this is a nice Q+ sensor, which has 4 electrodes now, 2 for the AFM, 1 for the tip sensor, and a 4th one for the excitation electrode. So you can do all electric excitation. The STM performance also got improved. This is a superconducting Josephson measurement with the aluminum tip and aluminum sample. If you look at the center peak here, the Josephson peak here, now this is on a microvolt scale here, 50 microvolts. You can see we can resolve that to better than 10 microvolts. So now we have kind of the perfect instrument that can do high resolution STS, both at near the base temperature of 10 to 15 millikelvin and AFM measurements. So we want to apply this now to this quantum Hall system and see what else we can learn from it. So now we're going to make a rectangular Hall bar, and we're not going to do the method we did before because we need a boundary that's really electrically insulated. We want a really physical edge, approaching a physical edge. So to do that, we've teamed up with Corey Dean's group, who is an expert in making devices, and they designed a multi-layer stack here with 2 graphite backgates. So we're still using a PN junction now to define the quantum Hall bar, where the outside gate can set the graphene to an electronic insulator. So we know graphene is fully gapped in the magnetic field, so that instead of having a physical boundary here where we cut the graphene, if you try and do that, we tried to do that, but the cut edge is all destroyed. It's all mangled up and has a lot of defects in it. So to have a continuous graphene sheet across the edge, we use a second graphite gate here, which sets this region to, instead of a vacuum insulator, we have an electronic insulator. And it behaves the same thing. You see the same quantum Hall physics. So this is the region of the Hall bar. This is the interior region, and then the outside is the exterior region. And so when we look at the edge states, we're going to go from this interior region to the exterior region. We can map the potential here across the Hall bar. And that's shown here. And you can see the potential boundary is very narrow. This is because we have the graphite backgate close to the graphene layer, so the potential is very sharp. So if you try to do, for example, the edge states with SETs, you wouldn't be able to resolve it because the SET typically has 100 nanometer resolution. So what I'll show you is that the same wedding cake profiles we saw in the PN junction rings, we'll see now in this potential profile. So this potential profile will get reconstructed into a step-like pattern. And what's nice with the AFM is we can measure directly this chemical potential. So we're not measuring Landau levels, we're measuring directly the chemical potential. And we do the same navigation, we have the runways. And now, in this particular sample, when you get to the graphene area, the first thing we noticed is that the STM measurements show that it has a Moiré superlattice. So this is an STM image. The larger lattice here is the Moiré superlattice of 3.5 nanometers. And you can see the graphene lattice superimposed. So we already know we have new physics or different physics going to come into play. When you have a Moiré superlattice like this, you break the AB lattice symmetry, and that's going to already give us a zero field gap. So we're going to start out with that Landau level 0 already being gapped at 0 field. So the degeneracy is already lifted due to this Moiré superlattice. So that's important to know. If you were to do transport measurements, you wouldn't know that that was the case, and you would, you'd have to kind of guess it. So we do the transport measurements. You can see here the resistance here, quantization, but you also see that the n equals 0 Landau level degeneracy is broken. So we can see that the normal degeneracy is 2, 6, 10, and now the 0 is broken up into plus or minus 0, plus or minus 1. So we want to see how can we see this in local measurements. And you could see this in STS measurements if you have the right conditions, but we wanted to see, can we see this in AFM measurements at these temperatures and at these fields? And the answer was yes. To our surprise, we were really excited. This is actually some of the first data that came out of the measurements. So this is now a frequency shift map. So we have a frequency shift. The AFM cantilever is changing frequency because of the force changing due to broken symmetry state. Okay, so you see these spikes here. This is the same region where the broken symmetry states occur. And you can see that a little more clearly if I just subtract a smooth background here, get rid of this background, which I'll talk about later. That's the chemical potential. And you can see the broken symmetry states have a frequency shift here in the bottom of about 20 to 30 millihertz. And if we subtract that background here, we can just replot this data. And you can see all the integer filling factors, both in the 0 Landau level and plus or minus 1 Landau level, can be resolved. And this is done now at 15 Tesla and 15 millikelvin. So the great thing about this is that this is now, we have a nanometer scale probe of broken symmetry states, which we can use to map out like edge states or do whatever we want. The other benefit of this measurement is that you get the chemical potential here. So we can measure all the energies of the Landau levels. And to see that, let's look a little more closely at the background here. So if we just look at the force curves here as a function of bias, you'll see I picked out 3 of them here. This is the standard parabolic response you get for a force curve, but the interesting thing is that this curve is shifting with gate voltage. The peak here, the vertex point, is when the bias balances the contact potential differences, right? So the vertex is the 0 force condition. And the reason why this curve shifts is that when I gate graphene here, I change the work function. So I'm shifting the Fermi level of the graphene when I gate it. And so this parabola is shifting. And if I just measure that vertex as a function of gate voltage, I get this step staircase. This is nothing more than the chemical potential changing due to the Landau level formation. And so we can read off directly the energies of the Landau levels, including the broken symmetry states. Now, this was done in a DC method where I just fit the vertex. You can do this much more better if I do lock-in measurements here and I modulate the bias here a little bit and do a very sophisticated lock-in technique. Then you can do this chemical potential mapping with much more fidelity. And that's shown here. So I'm doing now this AC Kelvin probe measurement. You see a bunch of Landau level plateaus and transitions. It just, we know it's graphene, so we can scale that. So we can collapse all that data onto a single curve. We scale it by square root of B. Remember, I told you the Landau level scale is the square root of B. We scale the density by B. And all this data collapses on the single curve. This is nothing more than the Landau level energies. So if I plot the density states of the Landau levels, you can see there's a 1-to-1 correspondence between all the plateaus and all the Landau levels. So we have a nice new Landau level spectroscopy tool with the AFM Kelvin probe measurements. And the nice thing about this is that this is done now without any tip gating. So because we're at the 0 force condition, we're at the balance condition where we nulled out the contact potential, we know we don't have any tip-induced density changes. Now, the data I showed you for like the quantum dot resonator was done with a tip that had a nice matched work function with the graphene, so there wasn't any tip-induced quantum density changes. But that's not always the case, and actually more than often than not is that you'll have an imbalance between the work functions. And in this case, it's actually an extreme case where the work function difference is 0.8 of a volt. You can read that off right from here because the 0 Landau level occurs here at minus 0.8 volts. So if we were to go now to 0 volts and try to measure this n equals 0 Landau level, we would have a huge gating field, and we see nothing more than quantum dot behavior. So it looks like we just created a quantum dot inside our quantum Hall system. So so in some cases, this Kelvin probe method is superior when you have these big work function differences. So we can just push it, see how far we can push this. We can blow up this region here. And we can see we can resolve all 4 levels of that n equals 0 Landau level I talked about in the beginning. So this is this n equals 0 Landau level where people are trying to figure out what phase, what is the ground state properties. And there are 2 aspects to this data. We have the plateaus here, E1 through 4. And then we also have this excursions here, these big swings in chemical potential. And these two signals come from the Fermi level moving through the different levels. So The plateaus come about when the Fermi level is partially in the Landau level. So these are partially filled Landau levels. So when we go from Landau level to Landau level, like this, we get a measure of these different plateau energies. Traditionally, transport measurements measure mobility gap, where they put the Fermi level in between the Landau levels, and they excite carriers and measure an activated temperature-dependent resistance change, and they try to extract the gap that way. When you do this, you actually polarize. When you put the Fermi level here, you can polarize the Landau levels, and that will add an exchange enhancement to the energy gaps and actually open them up. And that's what gives rise to sometimes these big excursions that you see in the chemical potential, exactly at these integer filling factors. It's when you get this exchange enhancement. So the advantage here with the Kpfm is that we can measure both these energy scales. And this is something that's not routinely done or even routinely calculated. So that's something I think that's, we can look at for more future measurements, and I think it might spur some more theoretical interest in these energy scales. But anyway, we can plot these energy scales. If we look at E3 minus E2 across the n equals 0 Landau level is the largest energy scale here. So that's consistent for what, for like a valley polarized gap. It goes up to, it goes as square root of B, like you'd expect for interaction physics, but then it kind of turns around here. And remember, I told you we have a zero field gap, sublattice symmetry gap due to the Moray superlattice. And so we know at zero field, we have to have this curve kind of has to go somewhere on this axis here, up here. So this is kind of gives us, more information on how this should behave. But the last few minutes I'd like to spend is now showing you how we can use the Kpfm measurements here as a probe of these edge states. So we can take the same measurement here, spectral measurements, and now I'll just do it as a function of distance as we go through the edge. Okay, and we should see those same compressible and compressible strips that we saw in the p-n junction rings. So that's shown in here. So this is a chemical potential map. So the color scale here is chemical potential. This is gate voltage, and this is Y position. So these are the plateaus you saw before. These are the big plateaus, the Landau level 1, 0, and -1. And then this is the boundary region where the dashed line is. If we cut across here, we can get the chemical potential profile shown in the middle here. And you can see it has that same step-like staircase we saw in the Landau levels. So this is, again, another measure of that reconstructed potential now directly measuring the chemical potential. So you have the compressible regions, the incompressible strips, and then you can calculate what you'd expect, from this paper here, and you can see that you get fairly good agreement with this length scale on the order of 30 to 40 nanometers. If we go a little higher in magnetic field, we can see better the broken symmetry states inside the n equals 0 Landau level. So here you have the 4 sublevels here. This is those excursions here that you saw before. If I blow that up, you can see that here. So here you see the whole states, the negative Landau levels going down, positive ones going up. But we can also follow the plus or minus 1 Landau incompressible strips here. This one goes up, this one goes down. And then we can compare that with what we'd expect from these different ground state symmetries. Now, if we look at the energy scales here, we see that it's fully gapped from the bulk into the boundary region. So we can kind of cross off this ferromagnetic case. We don't see any zero gapless edge mode as you see in resistance measurements. We can't really say which one, we can't really pin down a ground state configuration from this measurement. You need more information, like on the symmetry of the wave functions. And some of that has been done already by this group by Lee, who has shown some evidence for a Kekulé ground state. So there's more work to be done where we really need to combine STS wave function mapping with the Kpfm measurements to fully characterize these edge states. But anyway, I hope I give you a flavor of some new measurement frontier using AFM now at these ultra low temperatures and high magnetic fields. So in summary, I wanted to show you how we can create different p-n junction barriers in graphene. We can do that with the STM tunnel junction itself. We created circular graphene resonators, where you can see the Dirac harmonic oscillator states, and you can follow them at low magnetic fields and see this Berry phase switch turn on. We've created actually multiple quantum dots this way, which Daniel and Fresh has been working on. I showed you at high magnetic fields, these shell states transition into Landau levels, starting first in the center and then moving out. And then you get compressible rings and disks. Those compressible regions themselves are Coulomb islands and can undergo single electron charging. So your tunnel probe and your gate become a top and bottom gate where you can do sort of quantum dot charging physics. Then I showed you that we developed a new instrument that combines STM, AFM, and transport measurements at ultra low temperatures. We looked at how we can measure the energies of the broken symmetry states and map them across the quantum Hall boundary. And I think the AFM, has a lot of potential for future measurements at ultra low temperatures and high magnetic fields. So thank you for your attention. And I wanted to say hello to all my friends in the audience that I haven't seen in a long time.
Yep, thanks a lot, Joe, for this really wonderful talk and for showing us these amazing results. So as always, we have some time for questions now. So if you have any question, you can either raise your hand or you can write it in the chat.
Maybe I can. I was wondering about the energy resolution of the Kpfm. What is it limited by? Or?
It's limited by right now the noise of our amplifier. So the hard thing about Q+ sensors, you have to have a cryogenic amplifier, and its noise is given by to some degree how close you can place it. So we had to place our amplifier like about 1 meter away because you can't amplifiers don't work at like sub 4 Kelvin. So the amplifier is up here at 4 Kelvin. The STM is down here. So this is a little over a meter or maybe almost 2 meters of cabling. And that gives us a little bit more noise than you'd get in a 4K instrument. So I think we're seeing something like we can resolve on the order of maybe a millivolt or noise level, a signal level if we average. I'd like to do better. Because with the STS we can do microvolts. So the SET does a lot better, orders of magnitude better than the Kpfm. But it would be interesting to see if we can come up with some, sophisticated lock-in techniques or something that can do a better measurement of Kpfm. If we can get sub MeV, that would be great.
Yeah, thanks.
Thanks.
Maybe we take up to next. I think he has
yeah. Hi, can you hear me?
Yeah.
Okay. So have you looked at magic angle graphene by the combining both techniques, the transport as well as the STS?
Yeah, we're trying. So we've been trying for the past year to make the devices. So we haven't succeeded in making the devices yet. So we're close to making them now, but yeah, it's been a long road in actually making those devices. They're not easy. The yield is not high.
But there was a report that you have disorder in the magic angle. So I know it would be like a difficult hunt by the STM to verify that. But even that, you could not, spot any superconductivity yet, despite the fact that you may get.
There have been other groups working on that who've made a lot of progress. Ali Izdani's group has made a lot of progress in looking at magic angle graphene. We'd like to do the same thing and look for superconductivity as well. So the devices are being made now, but we haven't got them in the machine yet.
Okay, thank you.
Maybe next year.
Okay, But is there any, like, sorry, just one last question. But you did not observe any low-level excitation that could be like bosonic excitation as well with the STS, as perhaps an indication. I mean, if you are going to look for it, perhaps it would be nice to verify this kind of excitation, like the reason for superconductivity. I mean,
yeah, so we haven't done any measurements on that system, so no, I can't. We don't have any measurements to say anything about it.
Okay, thanks.
Okay, Sander.
Hi, Joe. Good to see you.
Hi, Sander. Yeah, good to see you.
I have a question about the early part of your talk where you showed this circular resonator. You achieve this potential by ion doping in the boron nitride, if I understand correctly.
It's natively doped. There are native defects in the boron nitride that you get.
Yeah.
And then we just park the tip above the graphene and we apply about 5 volts to it, and that ionizes these defects.
Right.
And so
the tip.
Yeah, so this picture here, so you just create a field above the graphene that ionizes the defects, and if you have the backgate field on it, it kind of draws the charge away, and then when you take the backgate away, that charge stays there. So actually, you have to be careful now. If you actually do graphene and you have your probe at like 5 volts, you'd be writing patterns all over the place. So
but how circular does this get, and how sharp is the potential? Is the edge of your potential well? It's I mean, you can play with the size scale a little bit by the distance where you pulse it, but typically we find them on this length scale, you know, of about 100 nanometer radius. But they're very smooth, and the sharpness depends on where you have the, you know, how much you dope it here. So this is you can see this is the maximum here is on an order of 100 millivolts, and then you can play with the background doping with the backgate. Right.
So we try to make this more or less symmetric. So the background doping is more or less like a minus 100 here.
But the shape of the tip is not important here. If you have an ugly tip, you still get a circular well.
No, I mean you'll get some funky shape too.
Right.
Yeah. But it's surprising in how smooth it is, though.
Yeah.
I didn't expect it to be so smooth.
Cool. Thanks.
There's another question.
We've made multiple ones of these where you can have like 2 parabolas very close together, and then look at and then you can actually go from coupled quantum dots to like a corral by changing the background density. And Faresh and Daniel has been working on that and writing that up now. I hope they're listening.
Thanks.
Okay, Leo next.
Okay, thanks. So I also have a few questions to the Kpfm. So the 1 millivolt resolution, that's really great. So what is your modulation voltage?
So we modulate at we look at the kind of the AFM noise spectrum, and you know it has like a lower noise level at low frequencies. So we're modulating between 1 and 5 hertz. So for these measurements in sample bias, we're modulating the sample bias to about between 1 and 5 hertz.
Yeah, with which amplitude?
Maybe like 20 millivolts, if I remember, something like that.
Okay.
Tens of millivolts.
Okay, and that's enough. I mean, it's very flat.
Yeah, that's enough.
Can I also add one comment? You said the nice thing about Kpfm is that you don't have any influence from the field. Of course, that's not exactly true, no? Because it's not a plate capacitor, so there might still be. I mean, you don't have zero fields. It's just smaller, but it can.
Well, it's a lot smaller than if you go to 0 volts with the tip. Yeah.
Yeah, but the work function as the tip can vary a lot as a function of position because you have a sharp tip. So I'm not so sure that that's a good simplification to say it's
okay.
It's null. It's null.
All right.
But
well,
let's discuss it. I'd like to understand it better. Yeah.
There was also a question in the chat from Alexis Baratov. I can read it out. And was the graphene one monolayer in the first part of the talk and two monolayers, or bilayer, with misalignment in the second part?
Yeah, no,
I think he's referring to the Moiré pattern.
Yeah, I'm sorry if that got that confused. So this was still a single layer of graphene, and the Moiré here is due to the graphene on the HBN insulator. So this is still single layer graphene in this part of the talk. The Moiré here is between the graphene and the underlying HBN insulator, but that still breaks sublattice symmetry and still opens up a zero field gap, as shown in transport measurements.
All right. I think what we could do now, I think there seems the burning questions seems to have stopped for the moment. So, Joe, if you have a few more minutes time, then what I would say is that we can stop the recording. Thank Joe again for the really nice talk. And then if people still have questions, you can stay online for a few more minutes.
Sure, no problem. So, yeah, I'd be happy.
All right, so thanks. That was really nice talk.